Sorry about that. Good morning, folks. How's everyone doing today? I'm doing fine, but I'm also questioning my sanity because I swear I saw a McDonald's commercial the other day. Yeah, I talked about this last time. I swear I saw a commercial that said like you can get like 2 bacon, egg, and cheese biscuits or McGriddle for $4. And like I finally cleared off my car, all the snow off, and went to McDonald's, was all excited, and they're like, "Oh, we've never heard of such a thing." And I can't find anything anywhere about this deal. So now I'm not sure if I didn't just dream it up or something. Like, has anyone else heard of this? I swear I saw this like on an ad before a Twitch stream or something. Like, no, so they have the sausage egg McMuffin 2 for $4, but that gets old. And the bacon, egg, and cheese biscuit is infinitely. They used to have the bacon, egg, and cheese biscuit as one of the options, but they took it off like a few weeks ago. I don't know. Weird. Okay. I don't know. Maybe I just got scammed. I don't know. Maybe so. Maybe so. But I could not find any information about it anywhere, so possibly not. Dude, it is. It is, especially when you have like nothing else. It's awesome. I was so excited, and I just had to eat my bacon, egg, and cheese, or my sausage egg McMuffin. Very disappointing. Okay. All right. So today, we're going to talk about quadric surfaces. Not going to go into too much detail. Basically, this chapter is essentially knowing how to plot what we call traces, which are cross sections of these surfaces. So if you know how to do that, and also being able to look at an equation and recognize which of these 6 surfaces that is the equation of, that is basically all you need to do for this chapter. So I'm going to go over how to graph these traces, what the traces are. I'll do like one example of these, but essentially I'm going to give you a sheet with the 6 quadric surfaces that has the equations of those guys, and basically just memorize the form of the equations. Like that's pretty much all there is to this chapter. It's one that doesn't show up too much later. I mean, we do some of the surfaces like paraboloids show up over and over. I suspect mainly because they're easy to draw, but yeah. Anyway. Okay, recording was paused somehow. Lovely. Okay. So let's, any questions about the traces? Does everyone understand what a trace is, right? We're going to have this surface and we're going to intersect them with these planes parallel, and we're going to get a curve. Those curves are the traces. Okay, so there are like three basic classes of traces. Of these quadric surfaces that you're going to get. And you're going to need to know how to roughly sketch these in very roughly. So like it should have a semi-recognizable shape, and you should get the intercepts correct, basically. That's all you have to do for these. So the first type you're going to see is an ellipse. Okay, so all of these traces could occur in the xy plane, in which case the equations will involve x and y, the xz plane, in which case the equations will involve x and z, or the yz plane, in which case the equation will involve y and z. We'll see how exactly we get that in a sec, but the equations are always going to involve just two of the variables. So I'll switch it up just to get you used to that, but hopefully that's not confusing. Okay, so ellipses are going to be of the form, or can be put in the form, let me just check that, x squared over a squared plus y squared over b squared equals 1. Sort of the standard form, all right? So it's two of the variables, both of them squared, they're both positive. And we have 1 on the right-hand side. If you don't have 1, then you just divide both sides by whatever you have. As long as it's not 0, we'll look at what happens if you have 0. And you can put it in the standard form. So ellipses are pretty simple. So this involves x and y, so we're going to graph it in the x and y, the xy plane. So basically, when you put it in the standard form, so you have x squared over a squared. So not a technical term, but everyone knows what I mean when I say this, and it's easier than talking about semi-major and semi-minor axis and everything like that. So the a squared in the bottom tells you how far in the x direction your ellipse is going, right? Your x radius. So we go a to negative a in the x direction. And the b squared, which is dividing y squared, tells us the y radius. So we go up to b, we go down to negative b. And that is your beautiful ellipse. And even something as ugly as that will get you full credit on an exam, because I could recognize that as an ellipse somehow. And I can see that the x radius is a and the y radius is b. I got the intercepts. So keep in mind, this is when the right-hand side is 1. Usually, we're not going to be too tricky about this, but yeah. So there's sort of something which I guess we sort of broadly consider an ellipse, because it can happen when we consider like a family of these guys. Don't even need to put that. Also, what can happen is, suppose we have, I don't know, whatever, x squared over a squared plus z squared over b squared equals 0, for instance. So you can have x squared, whatever, z squared, whatever, equals 0. So it involves x and z. We graph it in the xz plane. What point xz satisfies x squared over a squared plus z squared over b squared equals 0? What values of x and z satisfy this? They both have to be 0. So only the point 0, 0 satisfies this one. We still consider whatever that an ellipse, but it's not super important, but it's good that you know how to graph that. And also sometimes you can get something like this. So you get y squared. Let's do y and z this time. So you get y squared over something plus z squared over something equals a negative number. So it involves y and z. We graph it on the yz plane. So both sides, both y and z, both these guys are positive and are squared. So there's no number you can plug in for y and z, which will give you a negative number. So this trace can happen, and you just get an empty graph in that case. S for the top one. Oh, doesn't matter. Sorry, forgot the b squared. Just whatever's down there. Doesn't matter. So when you get something squared plus something squared equals a negative number, that's an empty graph, right? That corresponds to your trace not intersecting, the plane not intersecting the surface, right? The intersection is empty. So the point, the single point, that would be like, oh, hang on, that's not the one I want. That would be like this one right here, where it just barely touches the top at a single point. Okay, pretend that's a single point. So it sort of collapses to a point, and then that's going to be what you get there. And then when you go any higher than that, it no longer intersects your surface. There's no curve of intersection, right? The trace is empty. And that's going to happen when you get, something squared plus something squared is a negative number. Okay, so those are ellipses, right? Pretty simple. You've probably seen it before, just jogging your memory on how to do this. So ellipses are one type of surface, or sorry, one type of trace you could get, curve of intersection. Another type, which you should all be very familiar with, are parabolas. So familiar, in fact, that I'm not going to spend very much time on this at all. But for example, could have, say, x equals negative 3z squared minus 2, or something like that. Right, you have one variable by itself, not squared, equals something times one of the variables squared plus some constant. So this involves x and z. We graph in the xz plane. The important thing here is that you get it opening in the correct direction, your parabola. So it's either opening in the positive or negative x direction, the positive or negative z direction, and you get the intercepts correct. The fact that it's a negative 3z squared, I don't care if that looks exactly like negative z squared. Just that you get like the intercepts and the general direction opening. So x equals negative 3z squared minus 2. Which direction is this opening? Towards which axis? Positive negative x, positive negative y. Which one of those four? So you're saying negative z? So not quite. So if we had, if you think of this as x and y, right? If we had y equals x squared, right? Where x is the horizontal guy, it would be opening in the direction of positive y, right? So if we had like z equals negative 3 x squared, it'd be opening downwards in the negative z direction. but we have x equals negative 3z squared. So it's in fact opening in the negative x direction, like this. And the x-intercept is negative 2. Common mistake, but you just got to make sure you get it opening in the correct direction, you get the intercepts, and it looks vaguely parabolic, and you're good. Yeah. So that's what this one should look like. You've all seen parabolas, so I don't want to spend any more time on that. The next one you're probably the least familiar with. Those are hyperbolas. So we'll start with sort of a degenerate hyperbola. It's basically going to be a union of two lines. But if you have something like z squared minus y squared equals 0, for instance. So the graph of this, if you wanted to figure this out, you could just throw the y squared on the other side. So you get z squared equals y squared. Well, that is satisfied when z equals plus or minus y, right? So z equals y is going to be a line in the yz plane of slope 1. Z equals negative y is going to be a line in the yz plane through the origin of slope. First has slope 1. Z equals negative y has slope negative 1. And this guy is going to be just the union of those two guys. Just both lines together. Slope is not super important. We're not going to get out a ruler and make sure you get the right slope here. Just so you have the union of two lines through the origin. That's when you have one of the variables squared minus another squared equals 0. It's going to give you the union of two lines. That's sort of a degenerate hyperbola. So the general form of normal hyperbola is going to be like one of the variables squared minus another one of the variables squared equals a constant other than 0. So the way I remember how this works is always rearrange your equation so the constant on the right-hand side is positive, right? If you get a negative number, if you had like z squared minus y squared equals negative 2, then just multiply everything by negative 1. And then that becomes y squared minus z squared equals positive 2. And I'll tell you why. So what this is this is a hyperbola. The asymptotes are going to be these lines that we got from the z squared minus y squared equals 0. So those are going to be our asymptotes, those same lines. And then we're going to get a hyperbola that's either going to open up in the z direction and down in the negative z direction, or to the right in the y direction and to the left in the negative y direction. So if you rearrange this so that c is positive, the right hand, the constant is positive, the positive variable, the one that's not negative, minus, is going to be the direction your hyperbola opens. So if you rearrange so that the constant is positive, hyperbola opens in the direction of the positive variable. When I say positive, I mean the one that's, so z squared in this case, right? Plus c squared minus y squared. So z is the positive guy. That's our parabola, our hyperbola, rather. So it's going to approach the asymptotes, and it's going to open in the positive and negative z direction. And just to cover all our bases, the z-intercept, when y equals 0, the z-intercepts are going to be plus or minus square root c. And that makes sense, of course, because we rearranged it so that c was positive.
Was that plus or minus square root c or z?
C. Yeah. So you get the intercepts by setting, you're going to get z-intercepts, right? So you set y equal to 0. That's what happens on the z-axis. You get z squared equals c. Well, that happens when z is plus or minus square root c. So those are the z-intercepts. So for instance, if I had x squared minus y squared equals negative 3. So it involves x and y. It's going to be in the xy plane. I want to multiply everything by negative 1 because I want the right-hand side to be positive. So that becomes y squared minus x squared equals 3. And so our asymptotes are y equals x, y equals negative x. Sorry, that's really terrible. Those are asymptotes. And is it going to open in the y direction or the x direction? In the y direction, right? Because y is the positive guy. And then the intercepts are going to be plus or minus square root 3. Just got to label those. Don't really care about anything else. It's a vaguely hyperbolic shape, opens in the right direction, and I labeled my intercepts. That would be full credit for that guy. Okay, so those are your 3 types of traces. Your ellipse, which could also be a single point or empty. Your parabolas, which you know all about, and your hyperbolas, which could just be the union of lines if it's equal to 0. Okay, so let's do an example. And let me show you how we take these traces. So let's say we have the surface whose equation is x squared plus 2y squared minus z squared. Actually, hang on, don't like that one. So let's say we have z equals x squared over 4 minus y squared. Okay. So let's look at the traces. All right. So the traces are going to be X equals K, Y equals K, Z equals K. Right, so X equals K are going to be planes parallel to X equals 0, which is the YZ plane. And you can just let K be whatever. And so we're just going to kind of graph a, whoops, we'll see in a sec, Just let K be whatever, and we'll graph a generic one. Or let's do a specific example. Let me do a specific example in this case. Let's do a specific example. Let's do X equals 2. So this is the intersection of the plane X equals 2 with this guy. Okay, so what we do, so you go to your equation, you replace X with 2, and we get, because it's the trace X equals 2, we get Z equals 2 squared, which is 4, over 4, minus Y squared. I'll just write that 4 over 4 as 1. Now we have an equation involving just Z and Y. We're going to graph that in the YZ plane. Right, X equals 2 is a plane parallel to X equals 0, which is the YZ plane. And so we're just going to graph this curve in the YZ plane, and that's going to be the intersection with X equals 2. And that's how we're going to visualize it. So Z equals 1 minus Y squared. What kind of, is that an ellipse, a parabola, or hyperbola? It's a parabola. Okay. What direction is the parabola opening? Plus C minus C plus Y minus Y. It's opening in the negative Z direction, right? And the Z-intercept is going to be 1 in this case. So it also is going to have some Y-intercepts, plus or minus 1. We can do that just to be thorough. But that's going to be the trace X equals 2. So we intersect this surface with the plane X equals 2. We get this parabola. In general, for X equals K, when you let K be whatever, you're always going to get parabolas as well. You're going to get the equation Z equals replacing X with K. K squared over 4 minus Y squared. So what you're always going to get are just a bunch of different parabolas opening downwards. And changing the value of K is just going to give you different Z-intercepts, right? So you're just going to get a bunch of parabolas opening downwards with intercept K squared over 4, Z-intercept. But all these traces are going to be parabolas. Okay. So let me rewrite our equation. So Z is equal to X squared over 4 minus Y squared. So those are the traces Z equals K. Let's look at Y equals negative 2, that trace. Okay, so this is a specific example of one of the traces, Y equals K, but they're all going to be of the same form. Okay, so replace Y with negative 2 in your equation. We get Z, whoops, let me draw that over here. Is it Achieve? I'm currently on Achieve. It's up for me. Really? That's Not great. That's strange. I'm able to access achieve. I will have to look at that in a second then. Okay, well that's concerning. So I will check that after the end of lecture. Sorry about that. That's kind of weird. So replace y with -2, and we get z is equal to x squared over 4 minus -2 squared, which is 4. Same thing. We get a parabola. Which direction is this parabola opening? In the positive z direction, right? And the y-intercept, z-intercept is going to be -4. Okay, so if you really want to cover your bases, the x-intercepts are going to be plus or minus 2. And that's going to be our beautiful parabola. And then same thing in general, all of these traces, if you let y be whatever, are going to be parabolas opening upwards, and changing the value of k is just going to move these up and down. It's just going to change the z-intercepts. Oh, sorry, it's not going to be above. So that would be k equals 0, and then k equals plus or minus something is just going to move it down. No, because when you plug in x equals 4 and z equals 0, you get 4 squared over 4. Yes, I'm sorry, math is hard. You are correct. Thank you. Plus or minus 4. Coffee's still kicking in. Coffee's still kicking in. But yeah, you're just going to get a bunch of these parabolas when you change the value of k. Those are going to be the traces. So you can think of that y equals 0 is the xc plane. Y equals k. You're just, so y equals 2, y equals -2. You're just moving that along and then seeing how that intersects your surface. You're going to get these parabolas are going to be the cross sections in that direction. And then let's look at z equals k. Say z equals 1. Why not? So we go to our equation, replace z with 1. We get yeah. So if you want to get the intercepts, so the z-intercept, you replace x with 0 and solve. So solve for z. The y or the x-intercept, you replace z with 0, solve for x, basically. But yes, you could think of it that way. Okay, so we get x squared over 4 minus y squared equals 1. Ellipse, parabola, hyperbola. Which one? Not quite. So the ellipse has two squared variables, but they're both positive. It's going to be something squared plus something squared. This one has one of them negative. So it's going to be a hyperbola. So two squared variables is either, and positive is going to be ellipse. Two squared variables, one of them is negative, is going to be hyperbola. And one squared variable and then one non-squared variable is going to be a parabola. So we get a hyperbola here. It's going to be in the xy plane because it involves x and y. And the so we draw the asymptotes. I don't care about the slope. Technically, it's going to be y equals 1/2 x, y equals negative 1/2 x. Not important. Just two lines going through the origin. One of positive slope, the other of negative, the same slope. And is this one opening in the positive, in the x direction or in the y direction? In the x direction. Okay, so technically, okay, I guess maybe. Okay, so when I did the hyperbolas example, okay, so I can see why maybe this is confusing. So so with hyperbolas, it doesn't always have to be x squared minus y squared equals 1. They could have coefficients, right? So this x squared over 4 minus y squared over 1 equals 1 is still a hyperbola. It doesn't just have to be x squared minus y squared. It could be, they could have coefficients also. I could see where that's confusing. Okay, so it's opening in the x direction because that's the positive variable when we get the constant positive, which it already is. And so that's going to be a hyperbola. And the intercepts, to get the intercepts, you set y equal to 0, solve for x. So you get x squared over 4 equals 1, x squared equals 4, x equals plus or minus 2. Okay, so what I did before with the hyperbolas, not always going to be exactly of that form, but it's going to be two square guys. One of them is positive, one of them is negative. No, so the asymptotes would actually be, so what happens to get the asymptotes is instead of x squared over 4 minus y squared equals 1, you look at x squared over 4 minus y squared equals 0. So this is not that important because, like I said, we're not going to get out the ruler, to check your slope or everything. So to see what you actually get, right, you'd get y squared equals x squared over 4, or in other words, y equals plus or minus x over 2. And so those are actually going to be your asymptotes. But a positive guy and a negative line are just fine. Don't care too much about the slope. Yeah, I would say don't worry too much about that. The important thing is you get the opening correct, that it's a hyperbola, that it opens in the right direction, and the y, or the x, in this case the x. And the intercept is also, you should know how to do that, right? It opens in the x direction, not going to hit the y-axis, so there's no y-intercept, but it opens in the x direction. There's going to be an x-intercept. To get the x-intercept, you set y equal to 0, solve for x. So the way you determine the way a hyperbola opens is you look at the equation and you make sure that the right-hand side is constant or is positive, right? So if I had -1, then I would multiply both sides by -1 so that the constant became positive. And then it would become y squared minus x squared over 4 equals +1. So in that case, the positive variable, y, right, because it's minus x squared over 4, the positive guy is going to be the direction your hyperbola opens. How do you, so It's just, okay, so ellipses are going to have two squared variables, and they're both going to be positive. It's going to be something over something squared plus something over something squared equals 1. That's an ellipse. Two squared variables, both positive. Parabola is just one of the variables is squared. One of them is not. Hyperbola is two squared variables, but it's a positive and a negative. Yeah. Okay. Okay, so our surface was z equals x squared over 4 minus y squared. So when we intersect it with planes parallel to the YZ plane, we get parabolas. Actually, this was kind of misleading here. The z-intercept, it's going to be opening downwards. The z-intercept is going to be k squared over 4, right? So it's always going to be greater than or equal to 0. So those are our parabolas. That's what we get. And then similarly, when we intercept them with y equals k, planes parallel to the xz axis, we also get parabolas, this time opening upward. And then z equals k in general are going to give you ellipses, or sorry, hyperbolas. So when z equals 0, you're going to get the union of lines. When z is positive, you're going to get these hyperbolas opening in the x direction. And when z is negative, you're going to get these hyperbolas opening in the y direction. It's a family of a bunch of these guys. So this one in particular is difficult to visualize and kind of put together. But what we get is called a hyperbolic paraboloid. Oops. So remember that was z equals x squared over 4 minus y squared. And I'm going to attempt, foolishly, to sketch this. So that is, hang on, before I draw the axes, let me do it. So that's going to look like this. Oh, hang on. You know what? I used to be able to draw these, and I'm like drawing a blank here. This is why one reason why it's nice to have this on hand. This guy right here. It's going to look like this. Similar to that. It's going to be a saddle-shaped dude. So notice x equals k. So the traces are going to be in blue, green, and magenta. So the blue ones are going to be x equals k. Remember, we said those were upward facing parabolas. The green ones are going to be, no, the magenta ones are y equals k. No, okay, sorry. Sorry, the blue ones are z equals k. Those are your hyperbolas. The green ones are going to be x equals k. Those are the downwards facing parabolas. And then the magenta ones are y equals k. Those are the upwards facing parabolas. And that's how this all kind of fits together. Kind of hard to visualize, but really you don't actually need to visualize that. And you're never actually going to have to draw these in 3 dimensions. Really, you just need to be able to draw the sketches and to memorize basically a list of the equations of these guys, which I will send out to you. Let me show you. So it's going to be oh, don't be like this, Pinterest, for real. Really, dude. Okay, go away. But yeah, it's going to look like these, right? So you have ellipsoids, elliptic paraboloids, hyperbolic paraboloids, cones, hyperbola to 1 sheet, hyperbola to 2 sheets, and just memorize what the forms of the equations look like. So you can switch around the x, y's, and z's, but they're all going to have these types, and you need to be able to draw the traces, right? If I tell you, give you an equation and say, give me the trace y equals -1, you need to be able to do it like we just did, and then you need to be able to look at this equation and say, okay, this is hyperbola to 1 sheet or whatever. And I will send that out. So no, you're never going to have to draw a 3-dimensional surface. The most you will have to draw is the trace, the curve. And it just has to be a very rough sketch, right? You need to get the general shape, and then you need to get the intercepts right. Oh. Okay, hang on. Really? Okay. There we go. Okay. So is Achieve still down for you guys? Fantastic. Okay. So okay, well that's it for lecture. Let me end recording here.